और एक रवि मीना था तो उसका भी कहीं हो गया बात
को मैं तो पता नहीं है तो सबमिट कैसे किया
नहीं पैसा
अच्छा पहले तो वीडियो में है ना कॉपी चेकिंग वगैरह मिलते रहते हैं तो उससे इसलिए बताया कि मैं वहाँ पर
सर अपनी किस नाम से भेजा
अच्छा
एक हम लोग करवाएंगे 27 में
कॉन्फ्रेंस
रिफ्रेश करोगे
हाँ
अभी फेब में हो रहा है बट नेक्स्ट ईयर से जुलाई में होगा पहले दिसंबर में पीछे में दिसंबर में
अच्छा
इसमें
तो उसमें पेपर प्रेजेंटेशन ये सब भी रहता है इनवाइटेड
हाँ
जुलाई में तो फ्री रहता है
सोसाइटी में 2008
हो गया चालू हो गया
एक बार मैंने भी कराया था
अच्छा एक मिनट
नमस्कार आपको
अभी बस वेलकम तो 5 मिनट तो 5 मिनट जीतेगा तो वेलकम
क्या क्या बात है
लेकिन मेरा 3 साल के बाद
क्या हुआ
काम है
स्टार्ट दूँ मैं
ये तेलंगाना वालों ने जिनका अच्छा
Good afternoon, everyone. Good afternoon, everyone. I apologize for this delay. I would like to first introduce our session chair, Dr. Rajendra Kumar Ray, sir. Dr. Rajendra Kumar Ray is a professor at the School of Mathematical and Statistical Sciences, IIT Mandi, specializing in numerical methods for PDEs, computational fluid dynamics, and modeling mathematical image processing. He earned his PhD in mathematics from IIT Guwahati in 2009 and has published extensively in international journals and conferences. He has supervised several PhD students and contributed to nationally funded research projects. His distinctions include the IAAM Scientist Award 2024 and listing in Marquis Who's Who in the World 2015. He is a member of SIAM Islam, Calcutta Mathematical Society and the Indian Mathematical Society. So I would like to call Dr. Rajendra sir. Please welcome, sir.
Okay. So I think in this session we have two speakers. I think the first speaker is not here, right? Prof. Rashmi Bhardwaj is
Yes,
not
sir.
here.
She's sir.
Okay. So our next speaker is Professor Kumar Saha from NIT Agartala, sorry. So Professor Kumar Saha is a professor and head of the department of Mathematical and National Institute of Technology, Mathematics at the National Institute of Technology Agartala, specializing in optimization techniques, multi-criteria decision making, and computational fluid dynamics. He earned his PhD in mathematics from NIT Agartala and has published widely with a strong citation impact and an H index of 25. He is a gold medalist in MSc Mathematics, and he has guided several PhD students. He is a live member of the Tripura Mathematical Society and actively participates in national conferences and academic competitions. So I request Professor Saha to please give a presentation. It's a 30-minute presentation. As time is short, so
So, thank you, sir. I'll try to complete within time. And sir, sorry to say, this is some wrong information. Presently, I am not HOD because I have questions. Yes, no problem. Okay, fine. So now, thank you to the organizers for giving me this opportunity, and also congratulations to organizers for hosting such a great event. So my talk is here about solving interplanetary trajectory optimization problem. So what is interplanetary trajectory? Nahi chahiye? I am audible?
Yes, sir.
Okay. Okay. Thank you. So interplanetary trajectory optimization. So when a spacecraft moves one planet to another planet via some other planet. So that's it. Some missions like Cassini mission, Voyager mission, then Messenger mission, this type of mission has already started by NASA. And European Space Agency has remodeled those missions. And this is now an open problem or benchmark problem, so that in future this kind of missions can be expedited, or anyone can take this kind of mission. Now, what is the problem in that mission? As we know, we don't have that much of strong rocket or spacecraft that can move one planet to another place, say Earth to Mars, in a single go. For example, we know all about Chandrayaan 3. How long it took to reach from Earth to Moon? Any idea? Any idea, anyone?
depending on your engine.
No, our Chandrayaan 3 mission. How long it took?
3 months.
3 months. No, 40 days.
40 days.
40 days. So, but Russia, after us, they had sent a rocket and they reached there. Though their mission is failed, but they reached there within 5 days. So, what's the problem? What is the problem? Why could not make it in 35 days? Because of that, our spacecraft efficiency. Now, how it moves in 30 days? Because that much of fuel is not present, was not present in the spacecraft, which can run for 30 days. So, how that spacecraft gone there? Again, sir is today in inaugural session, the Professor Das was telling about Aditya mission. So Aditya mission took, again, any idea how long that mission took to reach from Earth, Sriharikota to L1 point? Almost 120 days. So how? So you cannot put fuel for 120 days in a spacecraft. So how it is possible? Because of gravitation of Earth. So they are taking the gravitation of Earth as a force and still some force from gravitation of Earth, and it has given a flyby. So there are several kind of rounds. First flyby, second flyby, third flyby, fourth flyby, and finally they reached in the mission. Now same thing when, say, from Earth to Mars is, nobody is between, I think. So say you want to go from Earth to, say, Mercury. In between Venus is there, so you cannot go to Earth to Mercury directly. So then you have to model it. So you have to use the gravitational force of Venus first, and then using gravitational force of Earth, using gravitational force of Earth, you can go to Venus. Then again, from using gravitational force of Venus, you can go to Mercury. Is it okay? So in that way, that this interplanetary trajectory problems works. So from here, उसमें जाना पड़ेगा कुछ ये है remote उधर जाना पड़ेगा. Okay, okay, no problem, no problem. So multiple gravity assist spacecraft trajectory optimization. So problem from name it is clear. This is multiple gravity assist spacecraft trajectory. So now, so okay. So I'll be from here. Is it okay? Okay. So now see. This is what I have said. Another interplanetary spacecraft trajectory refers to the path that a spacecraft follows when traveling from Earth to another planet or celestial body within our solar system. So this trajectory is carefully planned to optimize energy efficiency. What is the optimization problem? Because in this problem, I will go through so much of physics. Actually, space scientists can work whole their life about planning or about modeling these type of problems. So I am not a student of physics, I am a student of mathematics, so there will be a lot of physical terms. I don't know much of those terms, about those physical terms. Okay, so as a student of mathematics, what I know this is a problem of optimization. This problem has already modeled by European Space Agency, and this is an open problem. So I know this is an optimization problem, and I have to solve that optimization problem. And what is there behind this thing, what is the physics there, I know little bit of that, but not everything about that. And it is not my cup of tea also. It is not possible within that period I can know so many things of space physics. So this is, we have to optimize energy efficiency, travel time, and precise positioning for the spacecraft mission. For example, for Voyager mission, NASA has to study about 175 years of the positioning of different planets. Okay, there are a lot of celestial bodies in, so if your spacecraft is there and any celestial body attacks it or somehow it collide, then your entire thing will be gone. So that's why they have studied 175 years of the positioning of different planets, different celestial bodies. So this is not my task to go through those. So this is the model. You can see multiple, we call it multiple gravity assist deep space maneuvering. So generally we call it MGA-DSM when the problem will be within two planets, say from Earth to Mars or from Earth to Venus. And when there will be more than two planets, we will call it MGA-1-DSM. Okay, this is MGA-DSM where there will be only two planets will be related. That is, will be there only nobody in between. From say one planet, matlab we have to move from Earth and then from any other planet directly. There will be no planet in between. That is a MGA-DSM problem. And when this will be MGA-1-DSM problem, then this will be from one planet to another planet via any other planet. That is MGA-1-DSM problem. Now the problem is when this number of planets is more than 2, there is no analytical method, no classical method in our mathematical science till now that can optimize that part. So whenever the number of planets is more than 2, you have to optimize this with numerical methods. And for that, the population-based optimization or meta-heuristic or nature-inspired optimization algorithms are the best tool. So now this is the full the scope. See, there are planet P0, P1, Pi, etc. up to Pn. So these are delta V. So initial velocity delta V, V0, delta V1, etc. Then there will be DSM, deep space maneuver. I have already said deep space maneuver matlab you are stealing some force from the that is gravitation of that planet, and you are pushing your spacecraft to go there, to go to the next stage. So in this way, there may be, say, here for the sake of model, we have taken only deep space, only one deep space maneuver in between two planets, but there may be multiple deep space maneuver also. Because already we have seen in our Chandrayaan 3 or Aditya L1 that there are multiple maneuver was there. In Chandrayaan 3, I think 3 or 4, and in Aditya L1 there are more than 4 maneuver was there. So now this problem description. So MGA 1 DSM, I already told when MGA 1 DSM will be when the number of planets involved is more than 2. So MGA 1 DSM refers to one engine burn performed by a spacecraft in each leg of the flyby to alter the trajectory. And the entire journey you can divide in two phases. One is the tiny starting phase known as departure phase when it starts from Earth, and then the remainder of the trajectory or the unpowered swing by plane. Because after some time your spacecraft have no fuel. So you have to use the gravitation of those planets in between, or say initially for Earth, who can power your engine so that it can go further. So now there are so many variables you can see. For the first time period, let us take it T0. Then there will be hyperbolic velocity. There will be for second, third decision variables. Then departure, right acceleration angle. Then departure, declination angle, and the velocity magnitude of departure hyperbolic orbit. Now, if you tell me to tell about all these variables, then I will say that I cannot describe all these things. Okay, only I know about this. What are the things? Now, for the initial part, the heliocentric velocity of the spacecraft, when it is just starting, then it will be given by VSC. This is just notation, you can put other notation also. Now this is V planet, velocity of the planet, plus V0 infinity, and then this mathematical notation, because this is a three-dimensional part. So when psi equal to given, phi equal to given. Now for the rest of the journey, now it has started. So for the rest of the journey, that is the swing wise, the different maneuvers, that will be done by two parts. The calculation similar for each additional planet of encounter. Jitna bhi planet laga ho, this will be two parts. The first part is Keplerian propagation, we'll say Keplerian propagation, and the latter part by solving Lambert equation. Now, each additional planet adds 4 more variables. Already we have got how many variables here? See, 4 variables here with T0, then 5, 6, 7. So 7 variables. Now, if you put each additional variable, then 1, 2, 3, 4. So for each additional planet, you have to add 4 variables. So now, the first R, when we start, the first R, which is determined after the departure from any planet, is calculated by just our Newton's law of gravitation, and this is also known as Keplerian propagation, and the propagation will be for the time n into beta into t. Now second is by solving Lambert's problem. Now Lambert's theorem relates to two-body orbit determination problem. It defines a specific semi-major axis. So these are just physics. Let us know, because time is limited, so I am skipping this this particular mathematical modeling of those problems, how Lambert equations are modeled and solved. So these are this thing. So can I skip this physics part from here? So these are equations. Now the next term is determined by solving Lambert. So first part is by Newtonian theorem, Newtonian gravitational law. Second part is by Lambert's term. Is determined by solving Lambert's problem, which gives the initial velocity required for the Lambert. The DSM velocity of DSM, we are taking delta V, deep space maneuver, is provided instantaneously to match the propagated velocity of the Keplerian arc. Okay, so during the unpowered swing by stage, the craft's departing hyperbolic velocity is established by again two design parameters. So when from one planet, it will start from one planet then it is a hyperbolic velocity will take, and this hyperbolic velocity will be governed by two variables. This is one is called the swing by radius. So swing by matlab again from one planet to another planet by using the gravitation of that planet. So the swing by radius ratio and B plane insertion angle. Now these are some formulation. This is the swing by perigee radius. What is perigee radius? The minimum distance between an orbiting body and the center of the celestial bodies. This is a model is done by Izzo and Manuel Lopez in 2022. So now these two variable, one is incoming variable, another is outgoing variable. So incoming variable we are defined as V infinity in. So you can give name by another, and VSC already we have defined earlier. So here this VSC is there. So this is VSC in minus velocity of that particular planet. Similarly, outer velocity is VSC out minus velocity of that particular planet.
What is hyperbolic velocity?
When it is starting from a particular planet, this velocity is known as hyperbolic velocity. Say from Earth you have started, you are interested to go to say Saturn. So first you will go to say Mars. So from Mars it is starting, because it has to use the gravitational force of that planet. So whenever it will start, this will start by a hyperbolic way. It will take a hyperbolic way first initially. So that velocity is known as hyperbolic velocity.
So it will take a hyperbolic way.
Yes, initially, because it will again next round it will again take the velocity, that is take the force of gravitational force from that planet. So it will take multiple gravitational force. So it, just we say for just to discuss that it's still some of the velocity, some of the force, gravitational force from that planet. Okay. Now that is again, now someone can say that that if we steal from some velocity, from some force from there, then it will be slower. No, because that what we said now in class 7, 8, that by Newton's law the raindrop is attracting Earth. Again, Earth is attracting raindrops. So why raindrops are coming? Because of that mass. So that force, this gravitational force of that particular planet is so huge, and we are taking so less that it will not affect that particular planet. Now these are some turning angles, and this is in this hyperbolic velocity. There will be some eccentricity. So I am not going in details of these things. This is our V infinity out, V infinity, and to cos delta B1. So these are all the variables are defined here. These B1, B2, B3 are three unit vectors, and unit vectors are defined here. Then what we have to optimize. So our optimization task is to minimize Jx. So the Jx is delta Vd. Delta Vd is initially when it starts from the first planet. Then summation of delta Vds and jitna bhi maneuvering le rahe hain. So that is how many planets are in between, and then finally delta Va. Where delta Vd is subject to the constant delta Vd must be less than equal to delta V0 max. Now these are all your variables. Now depending on, you can see, depending on your planet, the number of variables will be there. N plus 1, T1, T2 up to Tn plus 1. Now if you have 3 planets, then there will be T1, T2, T3. Similarly RP1, RP2, RPn. So if you have 3 planets, you have 3 RP, then eta 1, eta 2, eta n plus 1. So in this way your number of variables will be increased. So this is the European Space Agency's Global Trajectory Optimization Competition, which was started in 2025 by European Space Agency's Advanced Concept Team. They have announced Cassini mission and Messenger mission as open problems, because these are highly nonlinear, and we have seen that already how many decision variables are there. Because if you have more decision variables, it is not possible for you to solve by any classical method or analytical method. So Now, because of highly nonlinear nature, these space mission problems are critical to solve using traditional methods when number of flyby planets, that is n, is greater than 2. Already I have said this, if number of planets is greater than 2, there is no existing analytical method which can solve it. You have to go for some numerical methods. Now Cassini-2 problem, already this is done, so it is easier for our modeling. So this is Earth, Venus. In Venus, this is 2 maneuver. From Earth, first it has gone to Venus, then Venus to again Venus, then again Venus it has come to Jupiter. From Venus again it has come to the gravity of Earth, then it has gone to Jupiter, and then finally Saturn. So a total of 22 variables are factored in that problem. This is the problem. Is it visible? So it has started.
So if it has to go from Earth to Jupiter,
Yes.
then it is going from Earth to Venus, and then Venus to Venus, and then Venus to Earth, then to Jupiter.
Yes. Now NASA has modeled that because they have seen, perhaps we don't know why they have done this kind of, because perhaps they have seen that this is the easiest way, because you have to see the position of other planets at the same time. Okay, when it is moving, so perhaps at that time Venus was near in the furthest side or whatever NASA has done in that way. So we have taken the same model as NASA. So it has started in 18 August 1999, and finally 18 August 1999, and finally it has, it has launched at 15th October 1997, and it has gone to Saturn orbit in 1st July 2004. So you can see from 97 to 2004 means it is 7 years. And now almost after say 97 almost 29 years. After 29 years, though the NASA has cancelled the mission, but it is still active. Last few months before, perhaps we have seen some news that this mission, Cassini mission, has given some signal to NASA. So still it is alive. Though they have now they are not getting fruitful data from this gene. Now similarly, Messenger. So Messenger, it was from Earth to Mercury. So Earth from the flyby sequences, Earth, then Venus. In Venus they have taken 2 times flyby, then Mercury first, then again Mercury second, third, fourth. This is the chosen flyby. So here total number of design variable is 26. So this is the mission. So first mission was started in 8 March 2004, and finally it has 3rd August. This is month, day and year. 3rd August 2004, and it has finally reached there in Mercury in 18 March 2011. So it has taken more than 7 years. So not more than 7 years, just less than 7, some days less than 7 years. So this is still, the NASA has abandoned their mission, but it is still active, though we are not getting any response from here. So now this is how to model this. So we have taken the help of meta-heuristic algorithm to solve this. Already there are, if you go to European Space Agency's website, you will find that what are the best results they have obtained till now. Though they have said that they are getting better result by differential evolution algorithm, and the result they have given in their website, we have performed the same from the that is the model, the code we have taken from there. The DE code is available everywhere, differential evolution code. We have run it 100 times, but we have not got the result even near to that what is reported in the website. I don't know how they have said that DE is giving better result. We have minimum run it for 100 times, but we didn't get that result. So whatever, perhaps somebody has got by some advanced machine. So these meta-heuristic algorithms are generally divided into, classified into 4 parts. It is called evolutionary algorithm, swarm-based algorithm, human behavior-based algorithm, and physical science-based algorithm. So out of it, we have taken swarm-based algorithm to model it. Anyone working on these algorithms? Now we have got slime mold algorithm to solve this. We have tried by slime mold. We have seen that the slime mold algorithm is not giving better result. So what we have done, we have tried to modify that slime mold algorithm so that it can give us better result. So slime mold, any idea what is slime mold? One kind of bacteria, microscopic organism, which is found everywhere and especially much in the ocean, but it is found everywhere. So based on
Nowadays,
this,
kids are playing with this slime. It's the same.
no. This is a microorganism. This is a microorganism, bacteria, very small bacteria. So this is how they search food. Okay. So this microorganism, bacteria, how they search food, that methodology has been mathematically modeled and used as an optimization algorithm. Thank you. So this is the microscopic view of slime molds. So this slime mold algorithm. So this slime mold algorithm is proposed in 2020 by Lee et al. So there are a lot of nature-inspired algorithms are there right now. Among them, so after 2018, more than 200.
5 minutes.
Okay, sir. So, after 2018, more than 200 algorithm has been proposed, and out of these, in 2022, Lee et al. Given this slime mold algorithm. Till now, this is one of the most popular algorithm that has been given after 2018. So I'm going a bit faster then because already sir has given me the time. So sir, maybe 1 or 2 minutes more. So this slime mold algorithm, this is the stage is divided by 3 phases. Okay, all algorithms actually works almost in similar way. First is you have to initialize population. That is again a similar method. We generally use lower bound plus some random number between 0 and 1 into upper bound minus lower bound. This is a special, though there are a lot of initialization techniques are there, but uniformly say 90% of initialization are governed by this principle. Lower bound of this variable, but it's a equation, we have already seen that we have 26 variables. So every variable has a lower bound and upper bound. So you have to take the solution as a vector with 26 element, row vector with 26 element, and each element will be choose by lower bound of that variable plus a random number between 0 and 1 into upper bound minus lower bound. So this is the first phase, and then this will be a search phase. So how these slime molds are searching the food for themselves. So this is first approach food. So they are approaching towards food, then wrap food, then grabable food. So first is, this is the first part, initialization. Already we have said, see, XL, NI, so N is for row and I is for column, because we have to take all at least 30 initial solutions. So this is lower bound plus a random number between 0 and 1 into X upper bound minus X lower bound. And then approach food. So in approach food, this xt plus 1, this will be through iterations. So t plus 1th iteration will be depend on tth iteration. So if there is a mistake, the second t plus 1 will be xt. Okay. So in this equation, this t plus 1, this is a mistake. So this will be only xt. This is the previous position. So xt plus 1 will be xb, matlab best position till now, into WA weight into XA minus XBT. Why that XA and XB are randomly chosen 2 solutions. Why? Okay, so I'll discuss it later. Then how to, when a random number will generate a random number, if that random number is less than P, then we'll choose the first equation, and if that random number is greater than or equal to P, we'll choose the second equation, and that P will be defined by this equation, tan hyperbolic SI minus DF. So these are all defined here. X represented by SI, best fitness is DF. Everything is defined here. So I can leave the presentation here for you. You can take it from say any of the organizers. Now, since time is less, I am going a bit faster. The formulation of VB already there is VBC. You can see VB is there. So VB is anything between minus A to A. So what is A? A is defined as tan hyperbolic inverse present iteration by maximum iteration plus 1. Generally, maximum iteration you can take 1000, 5000 or 10,000, anything. Then approach foot, this is smell index. And then wrap foot, this is the formulation of wrap foot, how to wrap the foot. First they are approaching towards the foot, then they are wrapping the foot, finally they are taking the foot. This is gravel foot. Now weakness, there are some weaknesses of classical SMA, because SMA is generally, we say that when number of variable is higher, then it generally trap into a local optimal point, optimal points. That is the main problem of SMA. That's why we could not get the good solutions by SMA to that Cassini problem and messenger problem. So that's why we have changed, or we have modified this slime mold algorithm by a little bit, not a little bit, by a quite higher way. So these algorithms this algorithm depends on two things. This nature-based algorithm. One is called exploration, other is called exploitation. Exploration means in this search area, say the search domain is there for the problem. In the search domain, whether you have explored the entire space or not. That is exploration. So if you have missed some, say some part of that search area, so maybe the global optimal solution may be. And another is exploitation. So till now, what the potential solution you have already searched, already obtained, whether near to them you have you have searched more or not. For example, I'm giving again small example. Sir, can you allow me for 5 minutes?
3 minutes.
Okay, 3 minutes. Say exploration and exploitation I am telling. So exploration is, say I have come here. So I am asking you, sir, who is from Delhi. So where I can visit in Delhi? I have 3 days in hand. So only 3 days you have given me these points. So I have moved those things. So only I have 3 days or 2 days. So I have visited some of the places. So I could not go to entire places, all the places which can be seen here in Delhi. So I have missed some. So I have explored, but I have missed some. That is exploration. So now, in a particular place, I went there. Because I have only 2 days, I cannot give more than 1 hour to that place or 2 hours to that place. Again, so in that place, a very good place when I can say I can go for at least 1 day, I have to visit that place only by 2 hours. That means what? I have missed so many places there, and which places I have missed nearby that, there could have been better place that I want to visit there. So one is exploration, whether you have explored the entire area or not. Another is exploitation. So within a choosing point, say you have already a potential solution. Within that solution, near to that solution, you have explored more or not. Okay. So any algorithm depends on the balance of these two factors. So what we have done, we have used first spiral exploitation. I am not going to discuss it exploitation. So from name it is clear we are using this for exploitation. So already जो हमें potential solution मिला उस so whether we have searched near that or not. Then refined exploration. So another modification we have used to enhance the exploration. So we are enhancing exploration, we are enhancing exploitation, and so that we can make a balance between exploration and exploitation. Now this is the pseudocode of this algorithm. Now, so whenever you will start an algorithm, you will devise an algorithm, first you have to check it, validate it, whether it is good or not. Where to validate? There are a lot of benchmark functions. And there are IEEE CEC, you know IEEE CEC, anyone? IEEE, you know everyone? So CEC, Congress on Evolutionary Computation. So every year IEEE gives some functions, and it is say competition. It starts a competition and give it to entire community. So you can devise your algorithm and you can check which algorithm is better. Okay, so this is a competition. First, second, third, they are giving this name. You have to give your algorithm, your result, and you have to upload them, and they will check whether what the result you are telling that you are obtaining, whether this is true or not. Now, if you are getting yes, your result is true, then they will go to competition and they will check where you are ranking. So now in 2019 competition we have used, there were 10 functions in that competition. Those are called composite function, hybrid function, rotated function, shifted function. So much complicated functions. All complication has been brought there within that 10 functions. So our algorithm, we have seen that this algorithm we have compared with SMA, LCA, SCA, MFO. These are some algorithms we have compared, and we have given from how much our algorithm is superior, from how much our algorithm is similar, and from how much our algorithm is inferior. So this is the performance table of the proposed algorithm. So then we have, so I can say that our algorithm is better than the other algorithm till now. So then we have used this in, these are some convergence. So we have shown that our algorithm converges faster than others. So now these are the variables of Cassini-2 mission, and this is the result. So first MSA you can see, so our is minimized. The mean result, standard deviation, and best we have reported. Our function was a minimization problem, so you can see that our result is minimum than so many algorithms. So similarly we have again messenger mission, we have again tested our algorithm to so many algorithms, and we have found that our algorithm is giving better result than other algorithms. So these are some references. So question please.
Thank you, sir.
First, so thanks for patience listening. Perhaps मैंने बोर कर दिया आप लोगों को ना.
So any questions from the audience?
Any question? And don't ask core physics question. I will not be able to answer. I am telling you.
Just out of curiosity,
Sure.
that in 2020 the Lee people, how they were motivated about that slime.
Slime, that is, I cannot say how they motivated, but actually we already said these methods, these population-based methods are classified into four divisions. One is this is called swarm intelligence or swarm-based algorithm. So in swarm-based algorithm, so many authors, they have taken some birds, some animals, some insect, even they have taken microbacterial organism. Now perhaps or someone from their field was maybe from biological field, so they have got that how these are working, how they search for. From there they have got motivated. Yes.
In SME algorithm, it is basically about how like it's for the searching food and all.
Yes, yes.
But I didn't understand how it is related to the space mission one. Means the logic behind
No,
this
no, no.
algorithm
This is not directly related. Yes, sit down. Please, very good question. This is not about the space mission. This is about starting an algorithm. Okay, so this is an algorithm. Now, how you have, that is secondary, because particle sum optimization of one of the most popular method. So that particle sum optimization is based on the food searching behavior of birds or fishes. Then ant colony optimization. These two algorithms are together with differential evolution. These three algorithms are so much popular that almost 90% application, industrial application of algorithms are governed by these two. So from ant colony you can understand these are based on ant colony. Differential evolution by human evolution, like genetic algorithm. Okay, so these are how you can construct an algorithm. This is nothing to do with a problem. In what problem? There are a lot of optimization problem. You can use this algorithm in any problem. The thing is to devise an algorithm. So this searching behavior of food has been used here to devise your algorithm. Now you have your algorithm. Now there is in equation you have some algebraic terms. Again, so those terms has been modeled by the behavior of slime molds. Now you have nothing to do with slime mold. Now you have your model with algebraic notations and equations. Okay, so now you have model. You can use this model, this algorithm, optimization algorithm, to optimize any kind of problem. Is it okay? Satisfied or not?
A little bit.
Actually, don't compare your slime, because you are taking the how they are searching. So searching model means it is some using some sort of algorithms. So you are taking the algorithm to solve this problem. So that is basically just you can say the mathematical replication of their way how they are doing that. So that can be used anywhere, because you are solving a mathematical problem. That is also the idea is used as a method that can be used for any problem.
After making the algorithm, you have to do nothing with those slime molds. Just slime mold behavior has been used to model your equations. Now you have only equations. You don't have now slime molds after getting the algorithm.
And another thing is the hyperbolic. Basically, they are using the angular motion to capture to get extra what is called this force. So if you use elliptic or other things, it will not give the force. So that's why they are using elliptic motion, so that direction
Initial direction.
Yeah, initial direction, which direction you want to get the force, that can be achieved. Just to minimize your what is called the fuel things.
No, there will be no fuel after some days. 7 years, so you cannot have fuel.
Yeah.
After some days, the
They
fuel
are
is
using
empty.
sunlight for their fuel, but still you need some force to that is called the escape limit. So you have to cross that. So that to do that you need some extra forces, and that is will come in due to the gravitational force using this hyperbolic tangential.
Even I'm surprised this hyperbolicity. We are doing theoretical kind of thing. There also it is hyperbolicity is found in much larger classes, and practically also, as you are saying, hyperbolicity, how they are
The
related.
thing is that so that means when you are taking the path, you are going very close to that, but suddenly you are going far, and again coming back. So this is basically giving acceleration. So if you see the the animation of how our this satellite, these things are done. So basically 3 times, 4 times, if you go, suddenly you can get a force that is escape velocity.
So you are taking force a bit from every motion, and finally you are giving a push to that. So because you have to cross the escape velocity, so you cannot go get that escapability in one go.
Okay, so I think yes, it is an interesting problem. So let's Saha.
Thank you all.
So do you have any next? I think this is
The
done,
last
right?
one. Now
Thank you, sir. Now we move on the memento presentation ceremony. As a token of our heartful gratitude, I would like to request Dr. Rajendra Kumar Rai, sir, to kindly come forward and present memento and certificate to Professor Abu Kumar Saha, sir.
Please, sir.
Wait. Thank you.
Thank you.
Thank you.
Thank you, sir. Now it is my privilege to invite Professor Mukesh Kumar Sharma, sir, to present the memento to Dr. Rajendra Kumar Rai, sir, as a mark of our sincere respect and gratitude.
The second one. The same thing in the morning. It's good. I like this.
Let's take note.
Thank you everybody for
This photo.
Yes, dear. Done.